Imagine a thought experiment. You sit in a chair wired to a quantum trigger. Each second, a single atom decays, or doesn't. If it decays, the chair kills you instantly. If it doesn't, you live. You pull the lever. You hear a click. You're still here. You pull it again, and again, and again. From your perspective, you can never die. Every time the universe rolls the dice, there is always some branch where you survive, and that is the only branch you will ever experience. This is the strange, unsettling idea called quantum immortality. Tonight we ask 3 questions. Where did this idea come from? Does the physics actually support it? And if it were true, what would it mean to be alive? In 1957, a Princeton graduate student named Hugh Everett III submitted a doctoral thesis that would unsettle physics for decades. He proposed that the bizarre behavior of quantum particles, being in 2 states at once, collapsing only when measured, wasn't really collapsing at all. Instead, every possible outcome of every quantum event actually happens. Reality, he argued, is constantly splitting into parallel branches. We call this the many worlds interpretation. In Everett's universe, when a radioactive atom faces a 50-50 chance of decaying, it doesn't choose. The wave function simply continues, and so does everything entangled with it, including you. One version of you sees the atom decay. Another version sees it remain stable. Both are equally real. Both continue forward in time, oblivious to the other. For most of the 20th century, physicists treated this as a curiosity. Interesting, perhaps, but untestable. Then, in the 1980s, a Russian-American physicist named Max Tegmark, along with others including the philosopher David Lewis, started taking the implications seriously. If every quantum outcome really happens, what does that mean for the observer? What does it mean for you? Tegmark proposed a now-famous thought experiment, the quantum suicide machine. The setup is grim, but precise. A gun is rigged to a quantum measurement, say, the spin of a particle. If the spin reads up, the gun fires. If down, it clicks harmlessly. The experimenter pulls the trigger. According to many worlds, the universe splits. In one branch, the experimenter dies instantly. In the other, they hear a click. Now here is the haunting move. The dead version of the experimenter has no further experiences. They cannot observe anything. But the surviving version continues. From that survivor's perspective, every trigger pull results in a click. Pull it 1,000 times, 1,000,000. The probability of any single survival becomes astronomically small, but in the branches where you exist to notice, you have always survived. You cannot, from the inside, experience your own death. This is quantum immortality, not the claim that you live forever in some grand cosmic sense, but the claim that subjectively, from the inside of your own consciousness, your stream of experience can never end, because there is always some quantum branch in which it continues. So is this real physics, or is it philosophical theater dressed up in equations? To answer that, we have to look hard at 4 pillars: the interpretation, the probabilities, the biology, and the measurement problem. First, the interpretation. Many worlds is one of several serious accounts of quantum mechanics. Surveys of physicists, including a notable 2013 poll by Schlosshauer, Koffler, and Zeilinger, published on AR-Quarf, show that the field is genuinely divided. Roughly 18% of polled physicists favored Everett's interpretation, while Copenhagen, decoherence-based views, and others split the rest. Many worlds is not fringe, but it is also not proven. It is one mathematically consistent way to read the equations. Second, the probabilities. Even within many worlds, not all branches are equal. The wave function assigns each outcome an amplitude, and the squared magnitude of that amplitude, the so-called Born rule, gives the probability we observe. Branches where you survive 1,000 consecutive lethal experiments exist, but their amplitude is vanishingly tiny. David Wallace, a leading philosopher of physics at the University of Pittsburgh, has argued at length that any rational observer should still weight their expectations by the Born rule, even in a branching multiverse. In other words, just because a branch exists doesn't mean you should expect to find yourself in it. Third, the biology. Quantum suicide assumes a clean binary. Either you die instantly or you survive intact. Real death is almost never like that. Aging is not a quantum coin flip. Cells accumulate damage, telomeres shorten, proteins misfold. These are bulk thermodynamic processes involving trillions of molecules, and at that scale, quantum branching produces essentially the same macroscopic outcome in every branch. There is no version of you in which entropy quietly decides not to apply tonight. This is the killing blow that physicists like Sean Carroll in his 2019 book Something Deeply Hidden have repeatedly stressed. Even if many worlds is correct, quantum immortality requires that there exist accessible branches in which you remain alive and conscious. For old age, no such branches exist with meaningful weight. The wave function does not contain a version of a 150-year-old you sitting comfortably in a chair, because the molecular pathway to that state is closed off by classical chemistry, not by quantum chance. Fourth, the measurement problem itself. Quantum suicide assumes there is a sharp boundary between conscious observer alive and conscious observer dead. But consciousness, as far as we can tell from neuroscience, fades. It dims. It fragments. The brain doesn't switch off in a single quantum instant. It degrades over seconds and minutes as oxygen depletes and neurons depolarize. There is no clean Schrodinger-style superposition between a thinking you and a non-thinking you. Researchers like Jimmy Jim Al-Khalili and John Joe McFadden have explored whether quantum effects play any meaningful role in the brain at all. The current evidence, summarized in reviews in journals like Nature Physics and the Journal of the Royal Society Interface, suggests that while quantum effects matter in some biological processes, photosynthesis, bird navigation, possibly olfaction, the firing of neurons is overwhelmingly classical. Your stream of consciousness is not a delicate quantum object teetering between branches. It is a robust, decoherent, thermodynamic process. So when you stack all four pillars together, what survives? The many worlds interpretation might still be true. The mathematics of branching might still be real. But the leap from all outcomes happen to I can never die requires assumptions that don't hold up under scrutiny. It requires a quantum trigger sharper than any real death, a biology more discrete than any real body, and a probability calculus that ignores how rare survival branches truly are. And yet, the idea refuses to die. Here is where things get strange, because some serious physicists have noticed something peculiar about the universe we live in, and they wonder if it might be a clue. There is a related concept called the quantum anthropic principle. It does not promise immortality, but it points to a softer, weirder cousin. The idea is this: any observer who exists to wonder about their existence must necessarily live in a branch where the conditions for their existence have held, including perhaps an unusually long string of survivals. This is not magical. It is selection bias at the cosmic scale. We only ever observe the universe from inside the branches in which we are still observing. Some thinkers, including Tegmark himself, have noted that we should expect, statistically, to find ourselves at typical points in our own life expectancy. If you ever find yourself improbably old, say, surviving against statistically impossible odds, That might be evidence that something like quantum branching is at play. But Tegmark also stresses repeatedly that he would never recommend testing this experimentally. The reason is simple. If many worlds is wrong, you simply die. And in the branches where you survive, you've abandoned every loved one in every other branch to grieve. This is the moral weight that quantum immortality carries. Even if it were true, even if some thread of your awareness persists in some impossibly thin filament of the wave function. The cost is the abandonment of nearly every version of you, in nearly every branch, to silence. Quantum immortality, taken seriously, is not a comfort. It is the loneliest possible form of survival. And there is one more twist. Recent work in quantum information theory, including studies by Wojciech Zurek at Los Alamos on quantum Darwinism, published in journals like Reviews of Modern Physics, suggests that the classical world we experience is not so much one branch among many, but the result of decoherence carving stable, redundant records out of the wave function. In this picture, you are not a single thread riding the multiverse. You are a robust, redundantly encoded pattern that exists wherever the conditions for it are stable. And those conditions, as far as physics knows, do not extend forever. So is quantum immortality real? The honest answer is probably not in any way that should change how you live. The interpretation it depends on may or may not be correct. The probability weighting argues against it. The biology forbids the clean binary it requires. And the consciousness it tries to preserve is not the kind of object that branches gracefully. But the idea matters because it forces us to confront something deeper. It asks what the self even is in a universe where the equations of physics may permit countless versions of every choice we have ever made. It asks whether mortality is a feature of nature or a feature of the particular mathematical structure we happen to inhabit. It reminds us that the strangeness of quantum mechanics is not just a laboratory curiosity. It touches the question of what it means to be here at all. Maybe the real lesson of quantum immortality is not that we live forever in some hidden branch of the multiverse. Maybe it is that this branch, this single, fragile, classical thread, is the only one we will ever know. And that is reason enough to pay attention to it. If you'd like to journey deeper into ideas like this, subscribe to Cosmic Edge.